you for coming to the seminar. So today we are very pleased to have my collaborator and also friend, Professor Akiko. He will talk. Here's a brief bio of our speaker. Dr. Akiko Taketa received her BS and MS degrees in administration engineering, which is basically industrial engineering, from Keio University, Yokohama, in Japan. And then her Doctor of Science degree in Information Science from the Tokyo Institute of Technology in 2001. And then after graduation, she worked in the industry for a couple of years, and then taught at the Tokyo Institute of Technology and Keio University, and also Tokyo University of Tokyo for many years as the assistant professor, lecturer, and associate professor, and now is a full professor at the Institute of Statistical Mathematics. And she will rejoin University of Tokyo in next month, right, as a full professor in mathematics again. And her topic today is household energy consumption prediction by feature selection of lifestyle data. So hopefully we can learn something related to energy consumption from a different perspective and also from a different country. So please join me in welcoming Professor Akiko Taketa.
Thank you for my introduction. And can you hear my voice? Okay.
Did you need the microphone?
Oh, microphone. Okay, I use this microphone, and I will give this. I will give a talk about this one, household energy consumption prediction by feature selection of lifetime data. So today's talk consists of two parts. One is the application of optimization method to energy problem, and second part is the algorithmic work. So if you have a question, anytime stop me. I will answer the question. So this is the joint work with my former students from University of Tokyo, my boss, and also company people at Tokyo Electric Company. Thank you. Okay, so my background is optimization. So I'm working on optimization research since I got during my PhD period, and recently I'm interested in applying optimization method to various areas like machine learning and energy systems. So that's why I'm very happy to be here, because lots of researchers are working on energy systems. Yeah. So I'm now applying optimization method to energy problem. And I'm working on these optimization methods so far. Robust optimization, bi-level optimization, polynomial optimization, and non-smooth, non-convex optimization such as sparse optimization. Today's topics, I want to talk about sparse optimization today. And my motivation is to find a better algorithm in terms of computation time and also quality of solutions for those problems. And as I said, this whole consists of two parts: application of sparse optimization to energy problem, household energy consumption prediction. And second part is algorithmic works on non-convex sparse optimization. So this is the contents of this talk. And I want to define what is sparse optimization. So this this is called sparse optimization program. And this program has L0 norm constraint here. L0 norm is defined, oh, why? Maybe,
Don't.
okay.
That's too much.
Yeah, and some animation.
When you're using the mouse,
Uh-huh.
when you're using the mouse, if you hit the click button, it will forward it.
Yeah, but I don't know why that it goes. Okay. Okay. No problem. If screen goes further, I just go back. Okay. Okay. Sorry. The L0 norm is defined as thank you. Defined as the number of non-zero elements in a vector W. So this requires that among n-dimensional suppose that W is an n-dimensional vector, and among them we want to find k non-zero elements. So this is called sparse optimization. And this function is not easy to be handled because it's a non-continuous function and non-convex and non-differentiable. So it's a difficult function to be dealt with. This is called cardinality constraint problem. And I will talk about this example later. But this problem is nowadays, it's a hot topics in machine learning area. So I noticed this problem a few years ago when I was involved in reviewing process for machine learning conferences. At the time, I suddenly had 8 publications from one conference. Then all of them are working on this problem. So I studied this program on the job training, and then I found interesting things. So I want to talk about this one from now on. This is an example of regression problem with feature selection. So suppose so the problem is to for household energy consumption prediction. We want to find a regressor having this constraint. This constraint requires that we want to find a k non-zero elements among n elements. So, we suppose that we have m households, and each household gives us this information. House type, family composition, number of air conditioners at the house, etc. And at the same time, we have household energy consumption. So we have n set of these features and also consumption data. And we want to select key elements, key important k elements from these features. So some feature may be irrelevant to prediction for energy consumption. So we want to find key essential k features among these features. So this is our problem. And okay. So this is the formulation I already introduced. And some people prefer to solve this problem by moving this constraint to the objective part. So both problems are called sparse optimization problems. And as a typical way of solving this problem may be convex approximation. So convex approximation approach was taken very actively in maybe 20 years ago or 15 years ago. At the time, convex approach was a typical way of solving these problems. But recently, So in this, as an application of energy system problem, I also took this approach. But recent trend in machine learning is to propose the non-convex approach for this problem. I will talk about later in the second part of this talk But for the first part of the application word for energy system, I took the first approach because if we take this approach, no-convex approach, the obtained solution always be a stationary point, which depends on the initial solution. So, application people, like company people, Tokyo Electric company people do not like solution which depends on initial solution. So if we show the results that selected feature like this, but it may be change it depending on the initial solution, then company people do not satisfy with the fact. So that's why I took this approach, convex approximation approach for energy system application. But later, as an algorithm part, I want to talk about non-convex approach later. Okay, so first, beginning, I will talk about application to household energy consumption prediction. So we want to predict the annual power consumption of a household using questionnaire about lifetime of household. So company people gave a lot of data from questionnaire surveys, and it was done for this period, 2 years, for more than 7,000 households. So those questions consist of these items: life stage, family composition, age, house type, etc., and home appliances possessed. For example, air conditioner, refrigerators, something like this. And also, the questionnaire asked how to use home appliances. For example, how long do you watch TV, something like this. A lifetime habit is about how long do you stay at home, how to spend holidays, outside person, indoor person, like this. So based on these questions, we made a model. So, but there are lots of missing data in a questionnaire survey. So we eliminated missing data samples, so remaining samples are this number. But yeah, of course, there are lots of machine learning methods for missing data, but this time I can just ignore the sample which has missing data. Okay. So the feature of our model is like this. So we found that the questionnaire data contains many categorical values. So I will explain it now. So for example, company asked this question to the each individual household, like what is the type of lighting in the kitchen? And there is multiple choices. One is fluorescent light, 2 is LED, 3 others. This value itself have no meaning. This, for example, 2 does not have any meaning. Nothing. It never imply twice more economical or something like this. This value have no meaning. So we need to do something for categorical value from 1 to 3. So it is expressed by a 2-dimensional vector. So if the K form chooses 1, then it's expressed like this one. So suppose that we have this is the residual function, and the coefficient A consists of A, I, J, M, and K form gives us this vector for the K row of coefficient matrix K. So we can express 1, 2, 3 by using 2-dimensional vector. But what we want to do is to select important features. So, but this one question consists of 2 vectors. So if this question is important, we want to select two variables corresponding to W1, W2 at the same time. And if this question is not important, those two variables disappear altogether. So for the purpose, group lasso is a very good model to express this sparsity, group sparsity. So group lasso was proposed by this guy, and they formulate group lasso like this. So this one is a group. So one, for example, the previous case, lightning question goes here, and suppose the second question has multiple choice, only two. Then one variable is enough. Dummy variable is only one dimension, and we can. This is the shape of this figure. This constraint area of this constraint, it can be drawn like this, and you will see that there is a sharp area around this one and this one. So optimal solution tend to be attained in such a sharp point. So suppose that you have, imagine that you have a contour of the objective function, and we want to find the point, the contour attached for the first time. And this sharp area tend to be attached by the contour. So this sharpness includes the zero value of this one or this one. So if the optimal solution exists around here, then W1, W2, this one vanish altogether. And if optimal solution attained here, then this guy will be zero, but this guy still appear altogether. So we can express this group sparsity by using this regularizer. So it's called group lasso model. So this is one feature. We use group lasso. And second feature, we found that power consumption is greatly influenced by season. So we use multivariate multiple regression analysis for this model. And using the so we solved three regression equations in summer, in winter, in other season at the same time altogether in one model. So this is the model, and if, for example, this red part is related to summer. So this is summer seasons, household data, winter season, household data, and other seasons, spring, autumn seasons data. And some feature is only contribute to summer, like air conditioner. We only use summer air conditioner in summer season. So this one is related to this part. And heater, it can be used only in the winter season. So this part contributes this one. And house type, family composition, it is not related to season. So it's a common factor for all seasons. So this matrix has a broad structure like this. So we use this model, and it's called multivariate multiple regression, because we can get all three regularizer all together at the same time. Okay, so this is our model, and when we have k questions in questionnaire, then the number of term is k, summation of k summation of L2 no. And okay, then this term express the group sparsity. We can just use our package called GG lasso. So GG lasso is for group lasso, and our model is multivariate group lasso, but we can use it. Anyway, so this is the size of our data, and we got this we got this numerical results. And this is a regularizer. And when we set a large value for lambda, then this solution try to give a less, try to select a few features. So if we set a lambda very small, then every feature will be selected. But if we set lambda larger and larger, then the number of selected feature is becoming small. And in the end, 1 or 0. If we set a too large value for lambda, then W optimal solution will be 0 vector. So no feature will be selected. So we can, by changing lambda slightly, we can give an order for all features. So it means it shows the importance for. So this results show that the number of air conditioner works have a big difference. Big difference to energy consumption, and also second, number of family members. So the company people said that it is a reasonable solution. These two guys are a little slightly related, because if number of family members is large, then a number of room will be large. The number of air conditioner will be increased. So maybe there will be relationship between these features. But anyway, the selected one is reasonable. Okay. And also we compared our method and the ordinary method. And the ordinary method is like this. At first, we calculate green part, and green part is fixed. Then next, red part is computed. After that, the blue part is computed. So sequentially, those solutions can be computed. So we compare this ordinary way of solving this problem and our method. And this is a slightly small difference. But anyway, we had a better results compared to ordinary method. Okay, so we proposed multivariate, multiple group Lasso model for energy consumption model. It works very well. And efficient algorithm is already applicable to our model. So now there is no room to improve algorithm for this model. But this is a trend in machine learning and non-convex sparse optimization. So now, using the remaining time, I want to talk about non-convex optimization method, because I'm very comfortable with talking about algorithm rather than application. Okay. So is it okay so far? I want to move to another topic, sparse optimization problem. So far I discussed about the convex modeling. From now, I want to talk about algorithm for non-convex optimization problem. This one, no using no relaxing this constraint. Okay, so this I want to explain this problem is equivalent to the above problem. So this part, this guy, is called largest K norm. And largest K norm is defined like this: the sum of large K elements of this absolute value. So suppose that we have already sorted element of W vector, and the top K element, sum of top K element is the largest K norm, and all sum of all elements is L1 norm. So if we calculate this part, it corresponds to the summation of the remaining part. So this constraint requires that all remaining elements should be 0. So in a sense, this constraint is equivalent to this equality constraint. And this equality constraint can be moved to the objective part if lambda is large enough, so-called exact penalty value, then this problem gives a solution satisfying this part equals to 0. So this problem is equivalent to the above problem. And this problem is called DC optimization. DC comes from difference of two convex functions. So this L1 norm is convex function, and large scale norm, this is also convex function. So this is called DC function, difference of two convex functions. And non-convex, this problem is called non-convex sparse optimization. So I already talked about the combination of this guy and this guy. So G1 is L1 norm and G2 is large scale norm. Then this problem is equal to this problem. But there are also other type of non-convex regularizer called MCP, SCAD, LSP. It's a very popular non-convex sparse regularizer like this. So all of them have this kind of splitting convex L1 norm minus some convex function. So we assume that we have this kind of formulation, and G1 is L1 norm, and G2 is some kind of convex function. Okay, so I already assume this part G is expressed as DC, and in most cases this is L1 norm and minus some convex function. And this one is called L smooth function. It's a very typical assumption for when we think of non-convex sparse optimization. So most of our researchers assume this constraint. This constraint means that gradient vector of F should be smooth L Lipschitz continuous function. So there is not so big jump for L function. F is not big jump. Okay. And okay, then there's a usual assumption. And based on this assumption, we want to propose an algorithm to efficiently find a stationary point. We already gave up finding a global solution for this problem because non-convex problem is too difficult to find a global solution. So we compromise with finding the stationary point. Okay, so using L smoothness property, we can split function F to DC decomposition, F1 minus F2, and both function F1, F2 are convex function. And already G1, G2 are convex function. So we could get a splitting of convex function and convex function. For this problem, DCA, so-called DCA, is a very popular approach to solve this problem. DC approach, DCA, is very simple algorithm to solve this type of problem. So this guy, beta minus beta is no concave function. So if we linearize this part, we have a convex approximation, right? If we linearize this part, then the resulting problem becomes a convex problem. So we linearize this part every iteration up to until the obtained solution becomes convergent. So we repeat this procedure until convergence. So it's a very easy and simple algorithm to solve DC problem. And already this property is known. So global convergence to stationary point is already guaranteed by this algorithm. But machine learning people do not like this algorithm because every iteration we need to solve some problem by using some software, optimization software. And if we want to solve a large-scale problem, it can be a bottleneck. It takes time. So, to resolve this issue, I propose the good way of DC decomposition. So I want to say that DC decomposition is not unique at all. Because, for example, we already have G1 minus G2 convex splitting. And if we add same convex function here and here, this is also another DC decomposition. So this means that DC decomposition will never be unique. So there are lots of choices for DC decomposition. So what I did is to propose a good DC decomposition to make this problem simple. To make this problem can be computed by a closed form solution. Then we don't need to apply software, optimization software for solving this part. So this is the secret of our method. And we propose this splitting DC decomposition. So it seems ridiculous because same function is added and distract from this equation. So it seems nonsense, but it works very well. So because of L smoothness of function f, this red part becomes concave function. And also already G2 minus G2 is concave function. So red part, this beta minus beta consists of these two guys, concave part. So and this is an example of L. So L smooth function. So L, if the given problem is convex, no, not necessarily convex. Quadratic function like this, then if we take L more than the maximum eigenvalue of G, then this part, this guy can be a convex. This part becomes convex. So we can get L easily for this case. And okay, so this is our proposed splitting DC decomposition. And now check what the subprogram is. So to apply DC algorithm for this problem, we linearize this concave part, beta. Then we get this problem. So take a derivative and linearize this part. Then you see that we have this problem as a subprogram. So this is a convex problem because concave part is linearized like this. And still, okay, and S, this part S is a subgradient of G2. G2 is not necessarily be differentiable. So if it's non-differentiable function, then we use subgradient of this function, right? Then this problem can be written like this. So this problem is, these two problems have maybe different objective function, but share the same optimal solution. So as mean is the same. You see that the equivalence by dividing all term by L and expand this norm, then W, the square norm of W goes here, and cross sum of these two terms goes here, and the square norm of this guy is just a constant term because it's already fixed vector. So this constant term disappears. And yeah, and G1 is the same with the above G1. So these two problems are equivalent. So what we have to do is to solve this problem. But this problem already, blue part is a constant vector. So it's a very simple, we know very simple calculation formula for solving this problem. So it's called thresholding operator for solving this problem. If G1 is given like this, L1 known. So now I'm focusing on L1 known here. Then after calculating this vector, just check the value of this element, each element of this vector, and if it's within this interval, set 0. If it's beyond this interval, then scaling like this. So this is the optimal solution for this problem. So we don't need to use optimization toolbox or software to solve this problem. We just calculate like this. We can easily get an optimal solution for the TIFF subproblem. So it's simple. And we compared our method with other existing methods. So these people formulate L0 known constraint like this. So they use that U, vector U is give a 0 or 1 optimal solution. If we combine these two constraints. And it's a big M. M is a large enough value M. So it's called a big M expression for expressing L1 constraint. This part, red part, is non-convex constraint. And those people also move this non-convex constraint into objective part by using a penalty rule. So this problem is equivalent to this original problem, and these people solve this problem by using a software. So, and also I forgot to write people's name here, but there is some people already proposed the best DC decomposition to get tightest approximation for every iteration. So the subprogram becomes a convex quadratic optimization. So those people also solve convex quadratic optimization by using a software, Cplex software. And in our case, we can calculate closed form solution, so we don't need to use software to solve some problems. That's why our method is quite fast compared to other existing methods. Because every iteration we just calculate a vector and check the value, whether the value is in the interval or not. So it's simple calculation, but other methods need to use optimization toolbox to solve each some problems. So that's why our method is quite fast. And also resilient a little bit larger than the smallest one, but not that big difference. Our method is quite fast. And, okay. And I'll hurry up and wrap up my talk. So I already talked about how to solve sparse optimization if there is no specific no constraint except this sparse constraint. But some programs, some applications have constraint, like C. So for example, sparse Markowitz portfolio model have a constraint, Cplex constraint at C. So some application want to incorporate some constraint, simple constraint. So as the next research, we propose a method how to incorporate, how to deal with simple constraint C. So in the previous approach, if we put C here, then no closed solution, no more closed form solution. So if we ignore this C, we have a closed form solution for this problem. But if we add this constraint, no more. So we proposed another DC representation for this constraint. and which erase this part. UT, this factory becomes really complicated, but without this term, it's a simple problem, just projecting this point onto feasible set C. So it also can be done by a closed-form solution if constraint C is simple enough. And this different DC decomposition is similar to smoothing technique for indicator function difference. So this is the secret of our method, and we formulated this problem by using indicator functions like this, and the smoothing. We use a smoothing technique for handling this part. So we also apply this techniques to more difficult problem, more general problems. So we assume more terms. Each of term have a simple calculation for proximal operator, like this one. So we can handle these constraints at the same time, and still some problem can be solved by a closed-form solution. So very fast, and we don't need to use a solver to solve the problem. So it's okay. So the conclusion: there is no much room for research on convex sparse optimization problem. So for application purpose, convex approach will be good because it's easy to explain. So we can get an optimal solution, and solution does not change depending on the initial solution. But non-convex approach is still depends on the initial solution. So sometimes it's difficult to explain why we get the features selected by the model. Selected features depend on the initial solution, so it's difficult to explain to the users, application people. So now we already have efficiency of the algorithm. So next target will be quality of the obtained solution. So finding a global solution is still difficult, but we need to find a better algorithm to find a better optimal better solution. No, stationary point, our method can find a stationary point, but not necessarily be good solution. So next target would be improve quality of the optimal solution. Okay. So that's it. Thank you so much.
Now we're open for questions.
I have a question. So, does the stationary point means the local minimum point?
Yeah, local minimum, and also okay, stationary point means like this. So this one is also called a stationary point. If gradient is 0, the point satisfying this condition is called a stationary point. So this point can be stationary point, this point can be stationary point, and also this point also can be stationary point. So local solution, we call this one is local solution, but not only local solution, but also this point also satisfy this condition. And our method might find this solution if it's a lucky case.
Question.
Question. Have you ever come up with validator? Have you ever come up with validator, or you believe all the data is right?
Yeah.
You believe all the data is right.
Yeah.
You're talking survey data, right?
Yeah.
Or this.
Yeah.
Well, sometimes you get the real data, and because of the communication or the conversion, there could be some bad data.
Yeah.
And bad data could have great impact on the result.
Yeah.
If you ever deal with bad data.
Yeah, thank you. Yes, today I did not explain anything about data, but we need to do phrasing for the real world data at first. Phrasing means that we check the outliers try to outliers in the real world data. And if we find something unusual data from the majority of the data, then we ignore the data. So we did such a procedure already creating to do a creating data. So outlier ignore and also missing data ignore. But there are lots of good machine learning algorithms to find outliers and also fill in missing data. So maybe next target we need to deal with such noisy data without just ignoring them, because our data sets become half of the original data by ignoring those such samples. And it's yeah, we should take advantage of all data by cleansing. So yeah, it's the next. Thank you.
I have a question. So when talking about the non-convex optimization, does the function has to be continuous derivative, or so is the function derivative continuous?
Yeah, this case not necessarily be differentiable.
Okay.
So yeah, so for example, largest genome, it cannot be. So I talk about the problem. Yeah, that one. This one is not differentiable. So we, in such a case, we just use a subgradient in the here subgradient somewhere. Here, we just use subgradient of G2 if G2 is not differentiable. So we did not assume any differentiability for G1 and G2, but for F we assume some differentiability because this property already assumed differentiability for F.
So how should we choose the regularization function?
Regularization function. Actually, this talk we did not specify regularization, so we can deal with any regularizer. So this regularizer is like this. So there are a bunch of sparse regularizer, non-convex sparse regularizers, and most of them are expressed as L1 function minus some convex function. So any regularizer, non-convex regularizer can be used for our approach if it is expressed as a G1 minus or convex minus convex regularizer.
Any other questions?
You mentioned about regression problems. Can you explain a little bit more? Because most of social scientists use regression.
Regression,
Yeah.
okay. Various kind of loss function. So regularizer, this one is one of loss function to make the best, to find the best fit for given data set. That's one of the regularizer. But there are different type of regularizer. For example, epsilon insensitive loss is just ignore small error and only give penalty for large violated loss functions. There are lots of loss function can be solved, and it's but it's still categorized as a regularizer. So your question is beyond.
In the beginning of your talk, you talked about some kind of issue in the regression.
Yeah, it's an example of our, so not necessarily this regularizer. And if F satisfied with this condition, else not condition, any function, we can deal with any function. The function F satisfy this condition. But application purpose maybe loss function like this regulation. It's simple to explain, but you're asking more another.
That's okay. We can talk about that.
Yeah.
All right. Mark, thank you for the questions and the answers. Let's thank the Professor Taketa one more time for